sneak back out toward the railroad track, toward the tracks themselves.
Yeah.
See some of the old rooms, and it was just fascinating.
Well, they've all been restored. It's a beautiful building.
Oh my, yeah, I've got to get up there.
I think it's working. Hello.
Morning, Tim. Morning, Richard.
Hey.
Morning, Dan. And
Hello.
I see
Hey,
John
everyone.
Nicholson is on too. That's great.
Let's see. There we go. Morning, Dan. Folks.
Well, good morning, everyone. So it is 10:01, and I want to go ahead and get started. We are now live on Facebook on our Kentucky AIPG channel, and I'll be sure to send the link after we're done. So for the February 2021 Diversity, Equity, and Inclusion series, we have a very special virtual tour of the Cincinnati Museum Paleontology collections, including the public-facing side at the Cincinnati Museum and Union Terminal, and the research side at the Geyer Collections. And so I will allow Cameron and Glenn to introduce themselves. Thank you.
I'll go first. Make sure I'm off of mute here. My name's Cameron Schwalbach. I'd like to thank you guys for joining me today. I'm the Paleontology Collections Manager here at the Geyer Collections and Research Center, run by the Cincinnati Museum Center. Thanks for allowing me to join you today and talk to you a little bit about what we do and some collections research.
My name is.
Oh, sorry. Go ahead.
My name is Glenn Storrs. I'm Associate Vice President for Science and Research here at Cincinnati Museum. I'm also the Withrow Farney Curator of Vertebrate Paleontology. So essentially that means I'm Cameron's boss. I'm responsible for the overall operations of the science side of the museum, but my training is in vertebrate paleontology, so I conduct active research. Today I'm in our public laboratory, and I'll be telling you a little bit about how that operates and what we do here.
All right, thanks, Glenn. I'll get started talking to you guys a little bit about the collection space. I spend most of my time here. If you guys don't know anything about a collections manager position, I spend all my time, my job is to curate and care for all of the fossils in our paleontological collection. I perform and facilitate research, both my own, and I facilitate research when professors and other researchers come to visit. I oversee any donations and incoming outgoing specimen loans. I also assist in the development of CMC exhibits and participate in some public outreach and educational programs to the public. I also spend a lot of time in the lab that Glenn will be speaking to you from today, where we prepare a wide variety of fossils, anywhere from microvertebrates and invertebrates to local Ordovician invertebrates to huge dinosaurs found out in the. But I'll let Glenn talk to you guys about that in a bit. So what exactly is the Geyer Center? If you guys have been to the Cincinnati Museum Center, you might not know about the Geyer Center. It's kind of a hidden secret, even to those in the Cincinnati region. It's a 70,000 square foot facility located just down the street from the Cincinnati Museum Center at Union Terminal. Here we house all of the natural history and history collections and history artifacts in the CMC's collections. So everything that's not on display, whether it be archaeology specimens or paleontological collections, zoology, history artifacts, and fine arts, everything is held here in the same building, each with its own distinct collection space and a controlled environment to ensure their preservation. In non-pandemic times, I'd be talking to you guys in person, but you'd also have the opportunity to see a little bit of this stuff. But for now, I'm going to skip straight to the fossils. So I'm in our paleontology collection space right now. Here we have all of our paleontological specimens housed in one space. That's vertebrate, invertebrate, and paleobotanical specimens. We keep things a little separated for a number of reasons, and things are organized differently, but everything is held here in one facility. I'm an invertebrate guy, so I'm going to start talking about invertebrates. First, I hope Glenn won't be too upset. Our collection space, our collections of invertebrates totals around 90,000 specimen lots. That sounds like a lot, but if you consider that any one specimen lot could have anywhere from one specimen to hundreds of specimens, the realization becomes apparent that we have close to 1 million or more fossils in this room easily. I'm not going to be the one to count them, but hopefully we'll have an accurate number here in the near future. On the invertebrate side, we have a large backlog of specimens, largely due to our inheritance of the Minnesota collection, which I'll talk to you about in a bit. But we're working through a large backlog. Invertebrate paleontological collection is organized according to the treatise on invertebrate paleontology. That is, it's organized taxonomically by groups of animals. This winds us around the room. I'm sitting right here in front of our peripherance section, and we wind all the way around the room to the far end, all the way to trace fossils and enigmatic fauna. Our focus of the invertebrate collection is lower to middle Paleozoic of North America, as you can imagine, us being in that region. We have special emphasis on the Cincinnati Arch region. As you know, we're world famous for Ordovician fossils of this area. We have specimens from Ordovician through Pennsylvanian strata, as well as Quaternary sequences from some of the glacial deposits in the region. But the bulk of our collection, the large bulk, is, as you might guess, from Cincinnati and Ceres Ordovician fossils. And this part of our collection is the world's largest and is unequaled in both its quality and quantity. In addition to our large permanent collection, we have over 5,000 type and figured specimens. I'll take you back here to show you a little bit.
Wait, can I flip it?
Yes.
Sorry, some camera help. All of our type specimens are kept in these fancy red cabinets. We have a lot of type stuff from anywhere from a lot of the famous type stuff from people you might recognize, like Ulrich. We have some poriferans. A lot of this stuff we got in the newly acquired Minnesota collection. These are some nice sponges from Ordovician equivalents in Minnesota. I'll talk to you guys a little bit about the Minnesota collection in a bit. We also have a paleobotany collection of around 25,000 or 2,500 specimens that was recently separated out from our invertebrate paleontology collection. Much of this collection is from Mazon Creek. You guys know about Mazon Creek. It has this nodular preservation. Trudy Hauser, a prominent amateur collector in the region, donated a substantial portion of this collection. Some of this exciting stuff, some Pecopterus from the Carbondale Formation of Illinois and Terre Haute, Indiana. These localities are world famous for their concretionary preservation of a variety of plant and animal fossils. We found there's vertebrates and invertebrates have been found in here in addition to plants, and I'll show you guys some of these in a bit. Just showing you some more Pecopterus. If any of you would like to see anything specific as I'm talking, feel free to request specimens and I'll do my best to hunt them down. So currently, during pandemic times, we are, as you might guess, operating at a little minimum staff. But we're pushing forward with the processing of the Minnesota collection. I spoke about it earlier. We've 2 years ago, we accepted the University of Minnesota's Orphan Collection. This is a huge collection spanning vertebrate and invertebrate paleontology, including upwards of 20,000 or so specimen lots. This is estimated, we've estimated this as over 50,000 specimens or so.
Camera, I think that it's on mute right now.
Sorry, how long have I been on mute?
It's like 15 seconds.
Oh, sorry about that.
I think when you're talking
talking
about the Minnesota.
I was talking about the Minnesota collection, and it's interesting parallels with our own Ordovician collection. Many of the prominent Ordovician collectors, such as Ulrich and Winchell and Schubert, and continued their study, stratigraphically similar fossils, and we have, just by happenstance, been able to inherit this collection and kind of parallel collections. I'll walk you guys through a little bit of the Minnesota collection. One of the coolest things about this Minnesota collection, Glenn has been working with our new interns. This site from, let me find my notes here. There's a couple sites out in Montana. The main one being the Bug Creek Anthill site. This site preserves a lot of microvertebrate fossils, both mammals and reptiles and amphibians. I'll let Glenn tell you guys a little bit more about this when you talk to him. But this anthill site is actually, these ants excavate the fossils themselves and build their anthills out of the fossil bits themselves, which are then collected by researchers. And we are now combing through a lot of unprocessed material from the University of Minnesota. What's really interesting about this is they're from the Hell Creek Formation. And if you know anything about the Hell Creek Formation, you know that it's right at the KPG boundary. So a lot of these are micro mammal fossils that allow us to see what's happening across this boundary at a very important time in geologic history. Just to show you these.
Cameron, all right, Cameron, I can jump in here just a little bit about the Hell Creek and the Bug Creek Anthills in particular. I've spent 6-7 years prospecting and collecting in the Hell Creek. It's a very famous unit, as Cameron said, at the Terminal Cretaceous, and has produced such charismatic fossils as Tyrannosaurus and Triceratops, which you see behind me that we collected out in Montana. Those 6 or 7 years produced maybe a dozen to 2 dozen Cretaceous mammal teeth, these micro faunas. They're the size of the heads of pins, some of them. The Minnesota collection, on the other hand, was discovered, this Bug Creek Anthill site was discovered in the early 1960s by the university and has produced literally thousands of these teeth. So it's a very, very important fauna, not only Bug Creek Anthills, but several other important localities which span that boundary between the Upper Cretaceous and the lowest Tertiary and Paleogene. So it is an important window on transition of faunas across the end Cretaceous extinction event.
What would you estimate that you were going through with this unprocessed?
I'm sorry, what was that question?
How much unprocessed material do you estimate that you've gone through so far from Minnesota?
Well, we made a first pass through most of the mammal material, as I say, thousands of them. But that first pass really means just sorting material into general categories, whether they're multituberculates, an extinct group of rodent-like mammals, or various therian mammals, marsupials, that sort of thing. The next step would be to go through and separate out those lots to genus and species if we can. That's going to be a long, long-term project. As I say, there are literally thousands of these fossils, but we've already received requests from many researchers, particularly in this country, who want to come and visit the collection to look at these specimens.
Okay.
Thanks, Glenn. Thanks for that.
Sure.
We also have some back to invertebrates, so I got sidetracked a little bit. We have several prominent paleontologists collecting and contributing to this collection. I mentioned Winchell and Ulrich and Schuchert. A lot of these guys have contributed type specimens that we didn't have in our collection that have helped us expand our collection a bit. The other thing we're working on, just pushing forward with, is the development of not only the Ice Age Gallery, which I'll show you guys a little sneak peek of, but we're also nearing the end of design of our Paleozoic Gallery focused on the Ordovician. And since many of these specimens are specimens I'd be showing you guys anyway, I thought we could take a little sneak peek at some of these. Now this new gallery is not just, we're trying to stay away from a typical show and tell style gallery, and we're focusing our story on the paleo environments and the paleoecology, and trying to get people to dive a little deeper into the information. And while it's going to be focused on the Ordovician, our gallery will span all the way through other Midwestern strata that we have, all the way through the Pennsylvania and Mississippi. So we get a representative of not just the Cincinnati region, but also of other things around the region. I am a Ordovician guy, so we'll start with the Ordovician. We have a lot of cool, rich. Here's a portion of our exhibit focused on the Richmondian invasion. As if you don't know about the Richmondian invasion, which I'm sure some of you do, it was an influx of over 50 new genera of species into the Cincinnati region during the middle of the Cincinnatian series. This influx, it was a lot of new taxa, a lot of new brachiopods, a lot of new corals and bryozoans. And if you look at the taxa in the early Cincinnatian compared to that of the late Cincinnatian, you can see a stark difference. Here's an example of some of these Richmondian invaders. One of the most prominent Richmondian invaders is this little guy. This is Grewinkia. Actually, this is actually a Streptolasma, but horned corals in general were not really around prior to the Richmondian invasion in any significant numbers. And corals in general are pretty indicative of the Richmondian invasion. Here's a Tetradium, which is not a coral per se. There's a lot of, this one's kind of up in the air now. Actually, I'm not sure of the currently accepted identification of Tetradium, but I believe it is some kind of algae. We also have some really nice cephalopods here. Another distinctive Richmondian invader is this guy, Characteroceras. Everybody knows Cincinnati for these straight orthoclonic nautiloids you see here. These are pretty common. A variety of taxa. This one here is Triptoceras, also indicative of the Richmondian invasion. These coiled cephalopods are a little less known. They're known pretty much strictly from whitewater deposits of the upper Cincinnatian, mostly nearshore deposits. But prior to the Richmondian invasion, these aren't very known. This is a particularly nice specimen. You can see the body chambers, and even the body chamber over here, starting about here. Some other distinctive invaders are some of these brachiopods, Hypertella. Platystrophia was more common during the early Cincinnati, and these wide-ribbed guys. You guys are all familiar with Platystrophia. Hypertella kind of took its place paleoecologically during the Richmondian invasion and thereafter. Here's some nice bivalves. Bivalve preservation is not very, compared to brachiopods, it's not very good in the Cincinnati, and this is due to the aragonitic composition of their shells. This one is particularly well preserved. You can see the growth lines of the shells even. And even the hinge line a little bit right here. Some bivalves, however, were composed of calcite rather than aragonite, so their shells are more readily preserved, such as this Carytidens right here. You can see the inside of this Carytidens. What else do we got here? Oh, here's a nice one. I'm sure you guys have seen Cyclonema gastropods before. They're a calcite-shelled gastropod of the Cincinnatian. This is a particularly large one. This is the biggest one I've seen. I'm not sure if anybody else has seen a bigger one. I'd be excited to hear about it, but this one was collected, let's see here. Arnhem Formation down in Kentucky from the Bull Fork Formation.
here.
Hey,
Here's from the Waynesville Formation. Although isotélus is not indicative of the Richmond invasion, it is very characteristic of the Waynesville, and some of the best and largest preserved isotélus specimens are from the Waynesville Formation. Here's some interesting crinoids, Plycodendrocrinus from the Liberty member, also Richmondian. I believe this one is unknown below an Edenian and Maysvillian strata. The back one, the little one. This is a cool collection. This is an entire slab almost made entirely of Zygospira brachiopods. Zygospira are pretty commonly found, and are often found in clusters, but it's kind of rare that you find an entire rock up with them like this in this concentration. So another portion of our exhibit is we're going to be examining different life habits. We have, you guys have, if you've visited our Geyer Center, or even if you haven't, you might know about the collection of the Florence 1 bed with the Egeo asteroid hard ground bed. A portion of this is going on display, and we're using it as an opportunity to talk about different aspects of the Ordovician life. One thing we're going to be talking about is storms and mudslides through the lens of preservation. As you guys know, high quality preservation depends very much on rapid burial, and that rapid burial is often due to storms and mudslides. This isotélus right here is maybe the nicest in our collection, donated by Dan Cooper and Ben Cooper. You can see right here, these structures are of the internal structure of some of the soft parts of isotélus, maybe muscle attachment structures as we're thinking. And up here, you can see the darker coloring on its cephalon. This is all pyritization due to early mineralization of the internal guts. So this is, as far as I know, as far as Brenda knows, this is the only trilobite from the area that has soft body preservation. So we're very happy to have this in our collection, and are really excited to put on display. Here's a little rare fossil. You guys probably can't see it too good because it's small. This is a Protoscolex. If anybody doesn't know what a Protoscolex is, I will not be surprised. It is an armored worm. And this is a unique specimen because it seems to be wrapping around a bryozoan. We're not really sure about what to make of this toponomically, but the occurrence of this Protoscolex and its preservation is pretty remarkable. It's a very rare fossil. When we're open, or when this exhibit opens, or even when Geyer opens, I encourage you guys to come visit, take a closer look at some of this small stuff. So this section of the gallery is a great opportunity to talk about incrustation. The slab that's being displayed, or the hard ground that's being displayed, has hundreds of Egeo asteroids, mostly Isorophus, but also some Stenaster and other Egeo asteroids. We're using it as an opportunity to talk about incrustation and boring and other feeding things. This is an interesting fossil right here. This is Catella calla. These might look like regular borings, but if you get close, you can see that they're kind of stellate shaped. I don't know if you can actually see it, but these are actually borings from a tunicate. Related to sea squirts, if you know what those are. Lots of different types of incrustation. Here's some Philhedra. These are inarticulate brachiopods encrusting the inside of a large, or the lower ventral side of a large Raphaneschina. Articulate brachiopods, or inarticulate brachiopods, are pretty cool. Very much different than articulate brachiopods. Here's some cool Cyphotripod bryozoans that I collected during my master's thesis. These are pretty boring looking little globular bryozoans, but if you look at the bottom of them, they have often perfect impressions of bivalves. It's really interesting because these bivalves would not have been preserved at all were it not for the encrusting of the bryozoan, because the bivalves, as I said earlier, have ragonitic compositions, they dissolve. So by growing on them, these bryozoans preserve the bivalves themselves. What else we got here? Oh, so you can, things encrust just about anything they can. Oh, here's a unique inarticulate brachiopod. Usually you find inarticulates encrusting something smooth like a Raphinaskina. This one's kind of cool because it's a big ribbed Platystrophia, but you still have all these encrusting brachiopods on it. And doesn't seem very, to me, easy to encrust something like a ridged brachiopod like this. We have a couple isotylus specimens, or sorry, Flexicolimene specimens that are really cool. So Flexicolimene is anything with moving parts is a little difficult to encrust. In particular, because those moving parts, once you encrust them, if they're moving, then your incrustation is going to break free. So when you encrust something like a trilobite with a lot of different skeletal elements, that tells you that it was, well, depending on how it's encrusted, you could tell a number of things. If the encruster is spanning over gaps in the skeletal elements, then you can assume that incrustation happened prior or post-death, post-mortem. Whereas if the encrusters are not going past the margin of different skeletal elements, you can tell that it happened in life. That is very clear here in this specimen. You can see this specimen right here where this bryozoan pretty much took over this cephalon of this Flexicolimene and overgrew its eyes. And if you look closely, I don't know if you guys can see it, but you can see the incrustation stops right here at the edge of the cephalon, telling us that the incrustation happened during the life of the trilobite. So for at least some amount of time, this trilobite was crawling around on the surface of the ocean, or on the surface of the seafloor with this big bryozoan stuck on its face. I really like encrusting bryozoans. I don't think I've ever admitted that before today. This is a cool one. These this is a famous Spathiopera. These encrusters are bryozoans that grow typically on the shells of cephalopods during the life of the cephalopod because of the alignment of these monticules. They go with the current that the cephalopod would have been swinging through. And the monticules, lots of bryozoans have monticules, and monticules are used to utilize Bernoulli's principle in order to create feeding currents for these bryozoans. Those monticules being elongate tell us that the monticules were in motion to create these currents. You guys aren't going to be able to see this one, sorry. All right, here's a part of our exhibit talking about molting and hiding. We also have, we're using this as an opportunity to talk a bit about our new prep lab exhibit that Glenn will be showing you guys in a bit. We're going to show a couple of fossils, both vertebrate and invertebrate, in various states of preparation. It's often that only the pretty fossils get displayed at the museum, and the public often thinks that we find them like this. We want to give a little insight to the science behind everything and show them the work that goes into finding and learning about and displaying these specimens. So we have a Flexicolimene here, as you might find it laying on the ground at an outcrop. Pretty good flexi, but it's still covered up, requires a lot of prep. We have a flexi that most of the matrix has been removed, but there's still some stuff right here in between the pleural segments. And then we have a final prep square specimen that has, it's pretty much to display quality where you don't have any extra rock matrix. But it's not often you get to see an unprepped specimen in the museum. And I think people around here would really appreciate that. This is a pretty cool specimen. One side just looks like a pretty poor cast of a cephalopod from apparently the lower Arnheim Formation. Flip it over and you have this perfect Flexicolimene preserved inside it. And cephalopod molds like this often have really well-preserved fossils because these sediments are sometimes injected into the shells and something like a trilobite might get stuck in there. Here's another one, arguably cooler. You can see on this side, just a regular cephalopod. On this side, we have an Acidaspis trilobite, two of them actually. Not only is this a trilobite, but this is an exceedingly rare trilobite in the Cincinnatian. So to have not only one, but two complete ones preserved here is pretty nice. Trace fossils can tell us a lot. They're often overlooked, but something like this tells us a lot about trilobites' behavior. These are all the trace fossil Rusophycus, formed probably by a Flexicolimene trilobite or another small colimenid. Trilobites often molted in aggregations in big groups and mated. So this is possible evidence of a trilobite molting party, as you might say. And you can see on some, if you get close on some of these, you can see the scratch marks by the trilobite segment or the trilobite legs. And you can see the clear bifurcation in the two lobes formed by the legs. Speaking of rare trilobites and hiding places, here's some small domal broken bryozoans. On the surfaces of them, you can see maybe these tiny odontoplorid trilobites. These are Primaspis trilobites, another rare trilobite in the Cincinnatian. Here's another couple large ones up here. These are often found in cryptic places like this. They like to hide under things, such as this bryozoan. So if you guys are ever out looking and see a boring bryozoan, be sure to check the bottom. It's always nice to see some perfect Flexicolimene trilobites. These are collected and prepped by the Coopers, who I'm sure you guys are familiar with. Can't show you guys any microfossils, but got some microfossils going into the exhibit. In my favorite portion of this exhibit, we're talking about the Cincinnatian environments, all the way from some of the environments near shore, like the whitewater and Saluda formations, all the way to some of the offshore environments like the Cope. And we want to talk about the differences in those environments, the fact that those environments exist at the same time in different locations, and we want to talk about how they're different, and the different animals that live in them and their evolution through time. So there's a major portion of the exhibit focused on the description of these environments. Here's some specimens from the offshore portion of this exhibit. These are really nice ophiuroids. I can't recall which formation these are from. These are from the Cope formation. Ophiuroids are known in the Cincinnatian, but very rare. You can see the preservation here is it's a carbonized film. So the actual the calcite material is gone. The calcitic material is gone, and only left these very fragile carbonaceous films. And these are actually really detailed. You guys probably can't see it here in my poor cell phone, but they're quite nice. Here's some more trilobite trace fossils. These are really interesting. Oh, we'll skip to this guy. Here's a really cool trace fossil. This is another Rusophycus. Rather than made by Flexicolimene, this one's made by Isotylus. We can tell this by both the shape and the size. There's not many Flexies this big. An interesting thing about this one, here you can see the little segments formed by the legs of the trilobite. The most interesting about this is this right here. This is a worm burrow, and a number of Isotylus Rusophycus associated specimens have been found associated with these intersecting worm burrows, and conclusions have been drawn that these Isotylus trilobites are finding these worms in the sediment and going down to get them out and eat them. And just so you guys know, this is the bottom. You're looking at this is a hypycnial trace fossil on the bottom of the bed. So this is the top of the bed. So you can imagine a hole being dug in the sediment to get to this worm burrow. Here's another Flexicolimene Rusophycus. Trace fossils in general are often impossible, or even are very hard, at least, to attribute to a specific animal or organism. It usually takes a case of association in order to do this, and this is one of those rare cases of association. This is a clear Rhizophycus, but if you look along the edges, you can see protruding edges of the pleural segments of a Flexicolemini trilobite. So this is an actual Flexi specimen preserved in situ with its trace fossil. It's really exciting. Here's some trace fossils of another trilobite that aren't as common. These are trace fossils of a Cryptolithus. Here's a Cryptolithus right here. He's a lace collar trilobite. It's a blind offshore living trilobite. Look, this is about as big as they got. They're pretty small. But their trace fossils are very distinctive compared to other trilobites. You can actually see the extension of the middle of their cephalon coming right here on all of these. There's like a little raised portion in the middle. One last trace fossil. I'll stop boring you guys with trace fossils. This one's really exciting. It's Astericides, named for asteroids. It's a starfish trace fossil. These are also very rare and really exciting. Sometimes we have another specimen here that I don't seem to see right now. You can actually see the movement of the starfish where it scooted across the seafloor and changed positions. Here's some more offshore specimens. Trilobites are very common in the offshore. They like the mud. They like to eat the stuff in the mud. Here's a small Isotylus, relatively speaking, very well preserved from the Waynesville Formation. Here's another different type of Isotylus. This is an Isotylus gigas, I believe. No, this is Maximus. This is gigas. You can see same genus, but very different features. This one looks a little more rounded with no spines, no genal spines. This one has very prominent genal spines and a little more of a triangular shaped cephalon. Here's a nice slab of graptolites. Graptolites are really cool, kind of enigmatic invertebrates that often leave these very small carbonaceous imprints. If you look really close, I don't think you guys can see it now, but they often look like little saws, like little saw blades. These are pelagic organisms that lived in the water column and are often used for relative dating in the Ordovician. So as we move from offshore Cincinnati environments to more nearshore environments, we get a change in the amounts of fossils we see, the types of fossils we see, and the types of rocks they're preserved in. So these are all preserved from deep subtidal environments, which is the next closest to the shore from the offshore. Here's another Acidaspis trilobite. So you can see there is some overlap of fauna. Some organisms are more tolerant than others of various environments. This is a Raffinaskina. If any of you have ever seen a bigger Raffinaskina, please let me know, because this is the biggest one I think I've ever seen. I could get a measurement for you. This one is donated by Trudy Hauser, who I spoke about earlier, who donated a substantial portion of our plant fossil collection. She's a prominent amateur dry dredger, or was in the 60s and 70s. I don't have a ruler right now, but if you know of any bigger Raffinaskinas, please let me know. We're looking for a bigger one. The deep subtidal preserves lots of nice, delicate organisms, often, because of the lower energy. The same reason that the nice preservation happens offshore. There's not much wave action to break things up. This right here is a Pycnocrinus, collected from Florence, Kentucky, by a couple of the dry dredgers. It's really nice preservation. This one is really exciting. This one was collected by Jack Kallmeyer of the dry dredgers. It is a holotype of Glyptocrinus nodosus. I'm not going to pick it up because it's on a very fragile piece of rock, but you can see we have a connected stem right here, and lots of delicate pinnulated arms splayed out. Here's a cool bivalve. This is Bissonychia. Ambonychia is a pretty common bivalve that looks very similar and has very considerably smaller ribs. This one has very prominent ribbing and is a little less common in the Cincinnatian. This one has particularly good preservation. It's retained some of its carbonate composition rather than just being a carbonate or carbon film. Let's see here. More Slabozygospiras. Here's a really cool Constellaria. Bryozoans are often overlooked because they're arguably kind of boring. Constellaria is one of the most common, or one of the most known ones. These monticules are in the shape of tiny 5-pointed or 6-pointed star shapes. I'm not sure the significance of the star shape, but the monticules, like I said earlier, were for creating feeding currents. Here's another large bryozoan. Some of these globular bryozoans created very mound-like body forms. Often you can see things preserved on the bottom like that bivalve earlier, but this one doesn't seem to be apparent in its substrate. I'm going too slow. All right, so as we continue to go, we have, so that was the shallow subtidal. We see more concentrated deposits. We see big wave-resistant forms, something that's not going to be beat up by waves, something like a big bryozoan or a coral. Something that can get stuck in the mud and stay there without being stirred up by waves. But as we travel closer to the shoreline, we soon get into the surf zone near the water line, and we have things like these huge deposits. This is from the Marble Hill bed. I'm sure you guys are familiar with the Marble Hill bed. It's a large paratidal deposit of almost exclusively gastropods, high-spired gastropods. This is attributed to lagoons near the shoreline of the Ordovician. Other things that have been attributed to this general paratidal environment are chemical signatures, things like this. We have right next to places where we're finding fossils, we're finding these barren deposits containing dolomite and calcite bugs. This is evidence of evaporatic environments, which would be evidence of the shoreline. There's some more, I know we're a paleontology trip, but you gotta appreciate some pretty minerals. Here's some nice calcite crystals in the same locality. These were found down on I-64 near Richmond, Kentucky. Some other nearshore things are things like this Solenopera, or I'm sorry, Pattersonia. These are algae. Sorry for the shadows, guys. These kind of look like corals and are often mistaken for them, but cross-section and examination under microscopes shows clearly that they're not. Here's a cool algae. This is a Dasycladacean algae. This is a very evidence of lagoon as well. You can't really see them that well, but these are actually carbonized impressions or films left of algae that was growing down near Owingsville, Kentucky during the Ordovician. We continue to go into the paratidal environments, and eventually we can find evidence of shoreline. We can find down near Richmond, Kentucky, mud cracks, Ordovician mud cracks like this right here. We can find these right down the street from places where we're finding trilobites and bryozoans and brachiopods and all these common Ordovician fossils. But just a few miles south, we have things like these mud cracks. We have tiny little scolitos burrows that you'd only find near shore. We have evidence of airly exposed sediments affected by waves. We have things like these stromatoporoids, these large sponges growing on the surface, both lenticular and globular forms. You can see the growth lines here. We're now in our weird and wonderful things. Here's a cyclocystoid, a very rare and enigmatic echinoderm fossil of the Ordovician. I'm not quite
I'm not very well versed in these, but they are fascinating and very weird. Yeah. I really don't know much about them. Sorry. Here's some more weird stuff that you guys will be excited to see. Here's some very well-preserved Eger asteroids, somewhat closely related to the cyclocystoid I showed you. Eger asteroids are encrusters. This one growing on what appears to be a tetradium coral, which is kind of weird to just have something growing on a coral. That it's not quite normal. Eger asteroids sat encrusted on their substrates, and although they're flat in their preservation right now, during life they were kind of like inflated little armored bubbles. They're echinoderms, so they use tube feet to filter microscopic particles out of the water for feeding. Here's some other ones. Those last ones I just showed you were Streptaster and what is it? Oh, Isorophus, and here's some Carniellas. Some other weird stuff. Ceramiporella, these odd donut things. They have a name in the literature. People used to refer to them as donuts, but they're encrusted cephalopod segments, cephalopod shell segments. So the cephalopod shell would have been preserved as an internal mold, and then that internal mold would have been reworked or broken apart in some way, and then individual segments of that would have been encrusted, eventually being found in these like weird little donut-looking things. Here's a really exciting fossil. This is Megalograptus ohioensis. It's the apex predator of the Ordovician seas, up to maybe 3-4 feet long Eurypterid. It had this is one of its front claws, if you can call it that.
That's just the claw.
Oh yeah. Not sure how exactly these guys or what exactly they ate, but these claws were almost certainly used in a predatory manner.
How big was the whole thing?
3 or 4 feet in total. Well, we'll have a life-size reconstruction of the Megalograptus in the new exhibit, swimming above your head in some way. This is a really cool fossil. This is a Cyclocrinites. By its name, its name might tell you that there's some confusion in its identification initially, and it was thought to be an echinoderm, but is now known to be an algae, which is really cool. Some algae, like this one in Receptaculites, if you're familiar with that, have very geometric patterns in their growth, almost reminiscent of the Fibonacci sequence in some cases. Here's another Pattersonia. I pulled one out earlier. This one's a little more prepped out. These are algae, globules that grow during the nearshore environments, or in the nearshore environments. Oh, some Dawsonia, named by Ulrich. Oh, this guy's cool. Enoplura. This is a very probably one of the rarest Cincinnatian fossils. Enoplura. That's hold it for me. Yeah. These are very idiomatic echinoderms. We have a couple here preserved. Here's another one. A little more of the body is preserved. If you guys don't know what one of these is, it's a idiomatic echinoderm. Here's a reconstructed one. They look pretty weird, and presumably they moved around. They aren't known from attachment structures, I don't believe, and had these two protruding little protrusions on the front of their bodies. I honestly don't know. Really cool though. All right, let me fast forward a little bit. It's not very known. The Ordovician around here is known as the sea without fish. If you guys have read the book by Meyer and Davis, it goes by that name. So it's often assumed that there weren't any fish in the world at this time. In fact, if you go to nearly equivalent strata out in Colorado and Utah, you can find things like fish bones like this. These are heterostrachan fish plates from the Harding Sandstone Formation out near Colorado, collected by Glenn Storrs, who you guys will be hearing from soon. So keep your eye out for some fish bones in Cincinnati. You'll be famous. Here's a cool inarticulate brachiopod, Traumatus, named for, I don't think you guys can see it, but its shell is almost, it has this perforated appearance. You can't see it. Darn. These are really cool. Here's a collected by Jerry Rush, an Iocrinus. This is a very nice specimen for a number of reasons. The main one being, I think, this is the preservation of its anal chimney. Many crinoids had an extended anal chimney to separate incoming and outgoing currents, because if you're expelling waste, you don't want to be retaking it in with your feeding structures. Is one of the prizes of the Minnesota, one of my favorite things found in the Minnesota collection so far. If you guys are thinking this is a hypostome, you would be correct. This is the hypostome of the largest known trilobite in North America, I believe. We measured this and extrapolated the measurements of Isotylus maximus and Isotylus gigas to determine a maximum estimated length. I don't think I have it right here right now, but it is huge. And it rivals the Isotylus found in Manitoba, Canada. I think it exceeded it by 3 or 4 inches after our calculations. But this thing is huge. This is from the Prostor Formation of Minnesota, which is roughly equivalent to our Cincinnati strata. Here's a really nicely preserved bivalve, Phalatomorpha. It's preserved as a very nice carbonate or carbon film, and you can see the ribbing right here. And that's not growth lines, I don't believe. That's actual ribbing structure on the front, on the outside of the shell. Here's some really unique graptolites preserved as white films on a black piece of slate or slaty shale. Sometimes the black shales preserve these white films. Rteocrinus. How am I doing on time? About an hour in. I better talk about some vertebrates, or Glenn will never let me take a tour, give a tour again. So although our exhibit is focused on the Ordovician, I alluded earlier that we had some other things available for display. So let me try and do it for a second. So we have a substantial portion of the exhibit dedicated to Devonian. Devonian, as you know, is the age of fishes. It's a major time in geologic history for evolution and diversification of fish. So we're trying to show various aspects of this evolution in some of our specimens. Here's a really cool little shark tooth. This one is found in Lorain County from the Ohio Shale Formation. This is local guy. What do we have here? Here's a Acanthaspis spine. This is a Devonian found in here in Ohio. You see the serrations. Here's a Cartopeltis dorsal plate. So many fish during this time were bony fish. They had bony plates. You guys are familiar with Thunkalosteus. The placoderms. Here's a nice Bothrio lepus.
Bothriolepis is a pretty famous fish. We have actually reconstructed Bothriolepis in our collection. More invertebrates. Here's some Silurian, I almost said graptolites, Eurypterids. Silurian Eurypterids are a little more diverse than ours in the Ordovician, and a little more widespread as well. Definitely the major predators in the post-Ordovician world were fish, at least in this part of the world. Here's a large jaw element from a Dunkleosteus turelli. Dunkleosteus didn't have teeth. You can see it had these plates that were pretty sharp. I don't know if you guys can see the edge there. Here's an Onychodus. This is a shark jaw element with teeth in place.
That's actually a Sarcopterygian, Cameron.
Oh, it is. Thank you, Glenn. My mistake. Here's a Heterostracanthus, Heterostracon. This is a pectoral spine. If you guys have any questions on any of this vertebrate material, direct them to Glenn. I promise he'll give you better information. Here's a tooth whorl from another Onychodus. 3 teeth in place. Plant fossils. We don't want plant fossils. Here's a quite famous cast. This is a Tiktaalik rosé. This is discovered in Saskatchewan, I believe, somewhere in Canada.
Nunavut.
Nunavut. This is a cast of the holotype specimen, which is located. Where's the holotype, Glenn?
Well, it was discovered and prepared at the Philadelphia Academy of Natural Sciences, part of Drexel University. But the specimen has now gone back to Nunavut, where a dedicated museum is being constructed to house it.
I'm sure you guys know about Tiktaalik. It's a major, quote unquote, transitional fossil in the evolution of tetrapods. I keep trying to avoid the invertebrates, but they keep coming back to me. Here's some Devonian trilobites. And huge bivalves. These are enormous internal molds of bivalves.
Well, if you want to avoid the invertebrates, Cameron, I could take over at this point. That's all right.
That'd be a good idea, Glenn. I was gonna talk a bit about the Ice Age exhibit, but I think I'll let you take over.
Yeah, well, let's do that. And if there's any time or questions later, maybe we can show you some of the fossils. But I think you've gotten a good taste of the range of material that we had, certainly from the Cincinnati Arch and the general Ohio, Kentucky area. A little bit of background. We are the largest, of course, paleontological collection and program in the region. 1 million or so invertebrate fossils, probably 30 to 50,000 vertebrate fossils. And not just Cincinnati Arch, of course. The collection spans the globe with fossils from every continent, excepting, I believe, Antarctica. We're still working on that. But what is the point of this collection, really? Certainly, we can use it to develop our exhibits, such as the upcoming Ordovician Hall. But of course, it's an active research program. It's a database, really, of the history of life on Earth. So scientists from around the world come to use this collection in addition to using the rocks in our area as a natural laboratory. So it's incumbent upon us to preserve these materials for posterity and to advance science either through our own research programs or facilitating the research of other individuals. Because we are are such a large collection with such great facilities, we have become a repository for orphan collections. Many institutions, particularly small colleges and maybe universities, are devoting their resources elsewhere. Of course, it's very, there's a lot of overhead, a lot of cost to caring for a collection like this and supporting a program. So colleges may be devoting time to teaching, for instance, and not so much to caring for their collections. So as a result, many of these collections from the region have come to us. Of course, the University of Cincinnati, Wilmington College, Wittenberg College, all those, their fossil collections have come to us. And Cameron has mentioned the University of Minnesota collection. A couple of years ago, they determined that they weren't able to properly care for this very, very important research collection of theirs. And we're looking for a partner to take it on. And because of the great interfingering or the way in which the collection complemented our own, because of the great Ordovician collection we have and the Canberra Ordovician of the Minnesota region, it was determined that they would transfer the collection to us. So that continues to happen. Our collection continues to grow. Cincinnati has the largest collection of paleontologists as well per capita in the country. There are 3 of us actively employed and researching here at the museum. There are 4 or more up at the University of Cincinnati. There are another 3, I think, retired in the region, all of which are actively cooperating. We have very good relationships with the local universities and also with the local amateur community, which sometimes is a rarity amongst museum and academic professionals. So we have the Drive Judgers, which is the local Cincinnati amateur group, and of course the Kentucky Paleontological Society based down in Lexington. These guys all do great work. As professional paleontologists, we can't spend our time constantly outdoors looking for fossils, much as we might like to do that, and much as the popular impression of paleontologists may be, but it's the amateur community, the dedicated folks who really get out there and find the important material. And a lot of that will be highlighted in the new upcoming exhibit. Now, Cincinnati Museum Center is an amalgam of a number of institutions, the forerunner of which dates back to 1819. So we're the oldest museum west of the Allegheny Mountains. And although we don't have paleontological specimens from that age, I think we still do have a few archaeological artifacts in our collections from 1820 or so. But the paleo collections do go back to the mid-1800s. As I say, they're continuing to grow. Other people who are conducting research in the region or even farther afield use us as a repository for their specimens so that the material can be, of course, observed and tested and repeated by future researchers. So a professor from Hanover College, for instance, uses us for his material that he publishes. We have a professor out at University of California, Riverside, who sends his material to us. So it's a very important collection. And the museum continues to grow. If you haven't visited us, we're in Union Terminal, Cincinnati Union Terminal. I encourage you to do so. The building has recently been completely renovated, and we are about halfway through developing the new exhibits to fill it. You've heard a lot about the Ordovician today. We're going to be opening our Ice Age exhibit with lots of new fossils sometime this summer. But our first exhibit that we opened was our dinosaur hall. And I encourage you to see that. There are 6 original dinosaur skeletons in the hall, each of which is an important research specimen and usually quite rare. We have one giant Jurassic predatory dinosaur called Torvosaurus, which prior to the discovery and installation of this skeleton at our museum was known only really from isolated bones or small accumulations of bones. We have the only associated skeleton of an individual Torvosaurus in the world, and it's exhibited right here in Cincinnati. So you should come try to visit. Now, we're not going to look at the dinosaur hall today. I'm in a laboratory that is associated with that exhibit. It's a public lab, meaning that it has a glass window. So I'm going to spin around here. You might be able to see some visitors passing by. So there is a window where folks can look into our laboratory and see active preparation underway. As Cameron mentioned, fossils usually don't come out of the field ready for exhibit or ready for study. They require careful cleaning and conservation, and that's done in this lab. And we want our visitors to be able to see that this is an active research program. We have an active paleo lab. We also have an active molecular genetics or DNA lab that people can look at here in the museum. You might be able to see in the window a line of large vertebrae. These are from the tail of another Jurassic dinosaur called Barosaurus. In the lab, there's a variety of equipment. So we have various ventilation and dust extractor systems to remove particles from the air to, of course, protect not only the equipment, but our lungs. And then active preparation tools, such as a glove box here, which under a microscope, in which one can use various pneumatic tools, such as an air abrasive machine, which is essentially a miniature sandblaster, where fine particles are expressed or projected under pressure to remove the matrix and hopefully not remove any of the fossil. Depending on the hardness of the matrix, different abrasive powders will be used. Typically, we use sodium bicarbonate, baking soda, which is relatively soft, but usually hard enough to slowly remove the matrix. Sometimes we have to go to harder abrasive powders, such as dolomite, for instance. Another pneumatic tool that would often get used in a glove box like this is an air scribe, which is sort of like a little pneumatic engraving tool or mini jackhammer. So again, under compressed air, vibrating tip, reciprocating tip, a small chisel or scribe can be used to remove matrix. We have also in the lab a variety of camera systems and monitors. So if a preparator is working in a glove box, for instance, an attached camera can show members of the public what is actually being done under the scope. And that's very popular for visitors, and a lot of questions rise from that. You might be able to make out in the monitor behind me some small microfossils. We talked a little bit about micromammals from the Hell Creek earlier. This is a collection of small shark teeth and fish scales and things like that from the late Triassic Westbury Formation of England. So we don't just work on microfossils. Here is a very fine skull of Triceratops from the Hell Creek Formation. And quite frankly, this is one of the reasons we started looking in the Hell Creek Formation, even though those micromammals are probably the most exciting research-wise, certainly very, very important and quite rare. People want to see dinosaurs in museums, and we don't have dinosaurs in Cincinnati because of the age of the rocks. With the exception of some Pleistocene material, we do have an Ice Age duck, for instance. And as you know, birds are living dinosaurs. So here's a complete Triceratops minus just the rostrum or beak and the nasal horn. But you can see the orbit or eye here. This is area of the cheek or called jugal. We have the big squamosals and parietals bones forming the frill behind the skull, and of course the brow horns. I guess the scale on this is about 4 feet, 4.5 feet across. We will likely restore the rostrum or beak of this animal for exhibit, but it has made a great exhibit in the lab. People have been very, very interested in the preparation of this specimen. It's quite a logistical undertaking to collect a dinosaur. This was probably a 2,000-pound block of rock when we brought it out of the Badlands in Montana. So it takes a lot of engineering, a lot of heavy equipment, plaster field jackets, reinforcement, et cetera. And then to get it into the lab and support it in such a way that could be observed by the public required creation of a steel armature behind it. Let's see here. A couple of other projects that are underway. I mentioned the microfossils. So here is just a small vial of tiny little shark's teeth. So that's one of the things that's being processed. Cameron mentioned preparation on fossils and how we were going to show the various stages of preparation. He stole a little bit of my thunder with one of the specimens I pulled out, because here's part of a colimitid trilobite with some of the early scribing that's going on to remove bulk matrix. And then in the future, an air abrasive likely will remove more of the matrix. This may not look like much here, but it is part of the upper jaw of Barosaurus, the big sauropod dinosaur whose tail is in the window of the lab. There's various teeth and such. It's not that well preserved, but considering there is no known skull of Barosaurus other than this one, it is pretty important. So this is just the tip of the snout, but we have more of this bone called the maxilla and a variety of additional bones of Barosaurus. We think we may have much of the skull. Part of it, another tailbone of a sauropod dinosaur. This comes from a site known as the Mother's Day site in south central Montana. It's Jurassic in age and has produced the remains of at least 16 small sauropod dinosaurs. You can see a composite skeleton of one of those, one of the smallest known sauropods exhibited anywhere here at the museum. And the other thing that you can see from our own research and excavation work out in Montana is an animal called Gallimiopus. This is a 50-foot sauropod dinosaur. Sauropods are those, Dino the dinosaur kinds of things, the four graviportal or pillar-like limbs, the long neck and tail, the big herbivores. And you may not know Gallimiopus by name. It's a relatively newly named in 2015. There are only 3 specimens that have been identified so far. Ours is probably the most complete. We have 85% of the skeleton. So I mentioned logistics with Triceratops. I think you can appreciate that collecting a 50-foot long dinosaur is a big logistic or engineering project. It took us 6 years to excavate that skeleton in the field. Bringing those bones back, piece at a time over the course of those 6 field seasons. The last block of which was 1.5 tons. Getting him into this lab or similar lab facilities at the Geyer Center, we spent another 7 years removing that from the rock with the sorts of tools that I've shown you around here behind us. And then 5 years to plan and develop armature and mounting materials to finally get it on exhibit. So it's a big, big project, but you won't see many Gallimiopus anywhere else in the world. Again, researchers from around the world come to use these collections. That's probably all I need to say about the prep lab and the history of the museum. And maybe at this time we can take questions, Cameron. I'm happy to talk about vertebrates if you're interested, or the museum. Say the Ice Age exhibit will be opening in the summer, and that features a lot of material from Big Bone Lick, Kentucky, which is the birthplace of vertebrate paleontology in North America, certainly really the Western Hemisphere, and it's one of the first documented sites in the world. So we have a lot of important material from there. We'll be showing a variety of other things. Cameron has now got some Ice Age material in front of you. Take it away, Cameron.
Hey, yeah. Yeah, please field, be happy to field any questions. Not just since Glenn mentioned, the Ice Age, I'll just show you a couple specimens. So large elk.
Yeah.
Glenn, how long did you say these specimens were separated that you found the pieces to?
They were separated a couple of years in the collection. They were found together, of course. That he's showing you two horn cores of a extinct steppe bison called Bison priscus. This was found in the permafrost of Alaska, and the sections of the skull actually fit together and will be exhibited that way. But they had been separated in the collection for some time, and thankfully, when we were developing this exhibit, they were reunited.
So it's always nice to reunite collection pieces. Here's some ground sloth bones, Jefferson's ground sloth. I think I heard you mention did you mention Thomas Jefferson?
You might have been imagining it, but Big Bone Lick was first actively excavated. It was discovered by Europeans anyway, in 1739 by a French military expedition. Certainly the Native Americans were familiar with the fossil bones that were common there for probably millennia before that. And indeed, they're responsible for the accumulation of a lot of those bones because it is a Native American hunting and butchering site. But in 1807, Thomas Jefferson sent William Clark of Lewis and Clark fame to the lick to excavate bones there that could be brought back to Virginia and Washington and studied. We have a letter that was written by William Clark from that expedition in September of 1807 to General James Finley, a prominent Cincinnatian, telling him what he was doing down there. You know, he was excavating elephant bones and bison bones and things like this. So very, very interesting stuff. At that same time, Clark also collected the first Paleo-Indian points ever found in North America. And while the bones went to Jefferson, those Native American artifacts came to us ultimately. For many years, they were in private hands and hence unknown to science. So what are now called Clovis points could have been called Boone County points or Big Bone points or something like that if they'd only been recognized earlier. But they are the first discovered, and we will exhibit some of those in the Ice Age too. We're now looking at a cast of bison latifrons. That's a cast from American Falls Reservoir in Idaho, but we won't exhibit that. We will exhibit an original set of horn cores from Brush County, Ohio, which looks like Cameron is charging to show you. These are original horns of an extinct bison with the keratin sheath. It'd probably be horns 6 feet across or so. This is from Brown County, Ohio, but the original holotype is a Kentucky specimen from maybe 15 miles south of Cincinnati, we think in the Wolper Creek area. This is from Illinoisan sediments. We will be exhibiting mastodon, of course. We have just received delivery of our complete mastodon skeleton. This was collected in the 1980s in Indiana. We sent it prior to the pandemic up to a workshop in Toronto, Canada, to have the steel armature prepared for it so that it could be assembled here in our museum. And it's taken a lot longer to get it back than we might imagine. Of course, the pandemic has intervened. So they weren't able to come down when we were originally scheduled to install it. More recently, they tried to bundle their trip with another American institution. And I will just say that delivery in January to Washington, D.C. didn't work. They needed to go to the mall and couldn't access it for perhaps obvious reasons. I'll leave it up to you to guess which institution they were going to be working at. So that was delayed. Just last week, they were finally coming down with a truck full of mastodon bones and steel armature, and were turned away at the border again because of the pandemic. So they had to separately ship it through a trucking firm. We have the bones and the armature now. We're just waiting for a Canadian technician to come down and help us assemble it. So it'll be an exciting exhibit. A lot of great fossils. We have an original Smilodon that is saber-toothed cat skull from the La Brea tar pits. We have a dire wolf skull. You'll be able to see those. Those are quite famous.
Glenn, why don't you mention the dire wolf tooth, formerly the bear tooth?
Yeah, so this is an interesting little story that highlights, here's the Smilodon and the dire wolf, but highlights the importance of maintaining a research collection. We had some researchers from Oxford and their partners in Australia come through a few years back, examining some of our Ice Age material to take isotope samples of the bone for which they could analyze isotopically to try to determine diet of these animals at a particular time. And we had in our collection a small incisor tooth, which was tentatively identified as a bear tooth. They sampled it, took their samples back to their labs, and recently you may have heard about the discovery, the genetic sequencing of dire wolf, which made a lot of popular press and was published in Nature just maybe a month or so back. And it turns out that they used 4 samples from across North America, and one of them was our bear tooth. Turned out when they sequenced it, it was dire wolf. And the sequencing shows that dire wolf, formerly part of the dog family Canis, is actually a much more ancient lineage and is separate from crown group Canis. There's a genus name of its own. So we're going to go back to the original name it was given before people started calling it Canis of Messiah. And that'll probably be the first example of that in a museum. That'll be in our new Ice Age hall. There's a woolly mammoth hare from Siberia. It's a lot of interesting things to see there. We'll talk about mastodon. That's a mastodon tooth. This is a mammoth tooth. Mastodon was first discovered at Big Bone Lick. That's the type locality for the American mastodon, an iconic Ice Age or Pleistocene mammal. Anyway, I don't want to ramble on too much about any of this. Again, I think if people have questions, because we've gone late already, if people have questions, we can address those specifically. So if you have, unmute yourself, and if not, it's been great talking with you. I hope you've enjoyed our virtual visit. Please come and visit the museum. We are open with safety protocols in place, social distancing and masks required, et cetera. So it's a very comfortable place to come and bring the family. Well, thanks so much.
I don't have a question, but man, I sure enjoyed this, even though I'm not a fossil person per se. But thank you so much. This was, I took plenty of notes because I do want to come up and see you. I hope everyone can find the time to do that.
We do as well.
Be most welcome.
Yeah, I'd like to mention, am I on here? Can you hear me? Yeah. I'd like to mention that we do this almost every year in person until the pandemic came along. So the Kentucky Paleontological Society does this every February, typically for our first field trip of the year. And maybe by next February, we might be able to do this in person. So please consider asking me if we're doing it.
Now let's hope we can all get back together in person next year.
Thank you very much. I've enjoyed it.
Great.
Cameron, I have one question. In the Ordovician collection, you mentioned that some of the fossils left behind a carbonaceous film. What caused that?
Well, the carbonized film, sorry, is left typically by the periostracum, which is a thin chitinous layer on the outside of like aragonitic shells. If you pick up like a mussel shell or any shell on the beach, you'll have the white carbonate material that the shell is composed of, and then you'll have a thin layer on the outside of the shell of the shiny colored material. And the chemical's signature left behind by that colored material on the outside of the shell is preserved in the Ordovician sediment rocks around Cincinnati as carbon film.
Okay.
So anything you see with a carbon film is either going to be something that was preserved previously, or that it was composed of aragonite, or something like algae that would have been composed primarily of carbon material.
Okay, thank you.
Okay, then. Well, again, thanks for visiting with us virtually. And hope we'll see you soon.
I'll see you soon, Glenn.
All right, Cameron, I'll see you next week.
We appreciate y'all's time.
All righty.
Thank you all so much.
Bye-bye.
Ann and Edward.
I do have one question before we hop off. It's education related.
Yes,
Do
please.
you work with student research projects at the undergraduate or even high school level on within a certain radius of the Cincinnati Museum?
Certainly, we work with students. Typically, graduate students work with us, but we have had undergraduates. High school students, it's difficult sometimes just because of the scheduling. Now, of course, currently the pandemic doesn't allow us to have student visitors. In fact, we're not accepting any research visitors at the moment. That's an unfortunate circumstance, but an understandable one from the pandemic. We have limited capacity. Even though we have big storage space, we're trying to maintain separate spaces. So Cameron is in there, I'm in there periodically, Brenda. We do have a few paid student interns, master's level students working with us at the moment. But we hope that in the future, again, when things sort of get back to normal, we'll be able to undertake some projects with students. A lot of them sometimes work with us in the lab here. We normally have a large volunteer crew in the lab, but again, that is not possible during the pandemic. So I'm able to be in here without my mask because I'm the only one in the lab. So we're limiting it to a single person at a time. But in the future, yeah, opportunities exist.
Okay, well, Glenn and Cameron, thank you so much again for your time on this Saturday. And I found it to be really enjoyable, like an extension of my own visit 5 years ago as a graduate student. And so thank you, and I'll be sure to share this link.
Sure, our pleasure.
Together.